The emission thing. The capture, the electron was in the reactant side. So let's look at these. What if I say write the nuclear equation for the beta emitter of cobalt-60? Can you set that up? Well, I know that it's going to be cobalt-60. And it tells me it's a beta emitter, which is 0, -1, B. Uh-oh, what am I missing? Atomic number, which is what? 27. So I have 60 is equal to 0 plus X. 27 is equal to -1 plus X. So what do I have over here? And what is 28? Ni. Pretty easy? What about the next one? It says, write an equation for protactinium-229 if it goes through 2 alpha decays. What is the element that is formed? So I'm going to start with protactinium-229. 229. Uh-oh, protactinium, I don't know what that is. Find it on your periodic table. What is it? 91. Does everybody agree with them?
Yeah.
And it goes through 2 alpha decays.
Wait, is palladium PD?
Palladium is PD.
Oh, okay. I don't know why I thought that was palladium for a second.
So what do you end up with at the first one? You have 229 is equal to 4 plus X. 91 is equal to 2 plus X. So what's on the top in the first one? 225. What's on the bottom?
89.
And what's 89? Actinium. So then my 229 actinium, or 225 actinium rather, becomes the reactant in the next round. So now I have 225 is equal to 4 plus X, and 89 is equal to 2 plus X. So what do you end up with on the bottom? 221 and 87. So what is the element that's formed? Francium or francium.
Yes.
Do you guys understand how to do that? It's pretty simple, right? Basic math. Everybody feels comfortable? I strongly suggest that you do a practice 1 or 2 on your own before you leave today, like the building. That way I know that you know that I know that you know that you can do your homework. Yes.
We need to do that twice.
Because it tells you on there that it does it 2 times, right?
But we can do 2 times that alpha.
No, you're going to do it because it goes through it twice. Huh?
Can I get some water?
Yeah, it goes through it twice. There's 2 more types of nuclear reactions that you have to know. So go ahead, I'm going to let you watch a cool little video because it's from the BBC and I really appreciate his accent.
Okay, like, when are we gonna just like drop a bunch of like
Huh?
It's not the old guy.
Oh no, it's not the cute little old man.
Are we just gonna like take all the alkali metals and just drop them in water? What is like the strongest alkali metal you can have
Atoms are
here
very
without
small,
breaking a law?
but there are 2 ways we can get enormous amounts of energy out of them. These are nuclear fission and nuclear fusion. Nuclear fission powers
We, like,
electricity
drop
generators.
potassium in water.
Okay, But nuclear fusion powers the sun.
Can we drop like
Fusion
a
wins.
drop of one?
But first, we'll look at
Like,
nuclear
this
fission.
much.
This means splitting atomic nuclei into smaller pieces. But not just any old atom will do. We need big ones. Uranium and plutonium are the business. Either of these can be used as fuel in nuclear reactors. In fact, particular isotopes of these elements work best. They are uranium-235 and plutonium-239. They both have large nuclei that split easily when we hit them with neutrons. Let's have a look at chain reactions. First, we need some nuclear fuel. We'll use this uranium. To start things off, you fire some neutrons into your lump of uranium. When a neutron hits a uranium nucleus, it splits into two pieces. This releases a lot of energy. A lot of energy. And it also frees 2 or 3 more neutrons in the process that zoom off at high speed. If they hit other uranium nuclei, they'll split them too, and so on. Each split sets off more and more reactions. This is called a chain reaction. Things could get a little out of hand, as you can imagine. Nuclear power stations use chain reactions just like this. Yeah, that is a bit scary. Of course, the rate of the reaction is carefully monitored and controlled with control rods that absorb some of the neutrons. This means the chain reaction goes along at a steady pace. Otherwise, the whole thing could snowball and it'd be curtains. Now, for something completely different, nuclear fusion, the other type of nuclear reaction. Here's the sun. It's really hot, apparently. The enormous amount of energy the sun produces is created by nuclear fusion. Fusion is the opposite of fission. Fusion is about joining atomic nuclei together, not splitting them apart. Here, we've got 2 hydrogen isotopes. Hydrogen 1 is just the usual type of hydrogen. But notice the surprise appearance of a neutron in hydrogen 2. In a fusion reaction, these hydrogen nuclei join to form helium nucleus. In fact, it's a helium-3 nucleus, not the usual isotopes of helium-4, which has 2 neutrons. In symbols, we write it like this. We include the mass number and the atomic number for each atom, so we can see exactly what is going on. The mass number is the total mass of the nucleus. That's protons plus neutrons. The atomic number is just the number of protons. Fusion reactions release enormous amounts of energy, much more than feeble old nuclear reactors and nuclear bombs. So it'd be a great source of energy for us humans. But no one has found a cheap, practical way to get fusion working yet. Nature can manage it though. All the stars, including the sun, are massive balls of fusion reactions. They release enormous amounts of energy, including light and heat, that reaches us here on Earth. Free energy! Great! But is this sustainable? Well, no, but don't worry. The sun won't be running out of hydrogen for quite a while. That's going to take a few more billion years. So don't change your holiday plans just yet.
So on your homework, you're going to have to be able to identify something as either a fusion reaction or a fission reaction. Remember, fusion, it's like fuse. Things come together. So a fusion reaction, you have 2 small things coming together to make a bigger nucleus. Whereas a fission reaction, you end up bumping something with a neutron to kind of start the reaction going. Any questions about that? All right, please do your homework. When we're talking about nuclear chemistry, we have to go and do half-life. Huh? Yeah, half-life by definition. So let's do half-life. Half-life is the time required for the amount of a substance to fall to half of its initial value. It's going to be, so we usually say half-life, and it's given by T 1/2. Notice how the 1/2 is lower. T sub 1/2, yes. Ah. And there's going to be a couple of ways that we can go ahead and do this. The easiest way is, let's go ahead and do a practice one. Does anybody know why we need to know half-life?
Rate of decay.
It's the rate of decay, yes. We actually don't know exactly how long it takes for something to decay, but because we have a lot of samples, we have a good general idea, and that's what we use. So let's do a practice problem that's not on your homework. Okay.
Will this be on our test?
It's real easy. You've been doing half-life there, and there are two ways to do it. There's going to be the first way we're going to do it is going to be probably the most simple way, and it's a safe way to do it. And it's just using a T-chart. I would write it out, yeah. So let's say, ding. So this is an isotope of CS137. What is CS137? What does 137 tell you? Mass number. And what's mass number?
The proton, number of protons.
Protons plus neutrons. Very good. If 1.0 grams of CS137 disintegrates, disintegrate means breaks down, so we're going to do this simple problem two different ways. So we have an isotope of cesium-137 has a half-life of 30 years. If 1 gram of cesium-137 disintegrates over a period of 90 years, how much remains? What that means is that how much did you start with? So I'm going to put down here number of half-lives, and then I'm going to have the amount here, right? So what's the half-life of it? It says 30 years. How much time passed? 90 years. So I'm going to take the time that's passed divided by the half-life, and that's going to tell me how many half-lives passed. How many half-lives have passed? 3. So to find out how much is left, I can set it up a little T-chart like this where I have 0. That's how much you start with. 1, 2, 3. So at 0 half-lives, when we started, how much did we have? No, that's the mass number of the isotope. How much of it did we have? 1.0 grams. Very good. In 1 half-life, how much is left? Half of that, 0.5. Very good. In 2 half-lives, how much would you have? 0.25. You guys are so smart. In 3 half-lives, 0.125. So how much remains after 90 years? 0.125 grams. Really easy, right? Now, making the chart is probably the easiest way to do it. Half-lives AMT, the amount.
Oh. So in here, when we're doing our calculations, sig figs don't count.
They do.
They do?
Sig figs do count, so it would have to have two sig figs, so it would be 0.13.
Okay.
Sig figs always count. This is just your example. All right, so now let's say that yes,
Why does it have two sig figs?
because we have 1.0 when we started.
So it'll always be
Yeah,
a
but-
sig figs of what is.
But it's not in the question, though.
1.0 grams? Yes, it is. It's right here.
Oh, okay, I get it.
Wouldn't it be 1.5?
No, it should have been 0.50. I just didn't write the zero after it.
For the 90 years?
90 years, how did we get here? Those are exact, right?
Oh, okay. So is 137 exact also?
137. Well, that's the mass number. How do we get mass number?
The number of protons?
Counting the number of protons and neutrons. If you count something, how many sig figs does it have?
0. Oh,
Infinite, right?
So
There you go.
if we were to do sig figs for this one, it would
It would have 2.
yeah, so we would have to make
0.13.
Okay.
Yeah.
Cool.
Here is, for those of you who are like, ugh, I'm not drawing a chart that is totally beneath me. No, not totally beneath, totally beneath me.
Shots fired.
I want you to go ahead and write down this formula. You have A is equal to A sub 0, which we call A null, times 1 half T raised to the power of T over half.
So long.
T over what? N?
I just thought
T over H.
What's that?
Well,
I just thought it was null because of computer science.
you should. That's the same thing. It's null.
Thank you,
Yeah.
I just thought he was saying null, and I was like, wait, why would
Yeah.
Zach understand AP computer science?
Exactly.
And then I realized. Exactly.
So A is our final amount. A null is going to be our initial amount. T is the time that's passed. And H is your half-life. So did everybody write that formula down?
Oh, that's H, not N.
That's an H.
Is this the same thing we just did or no?
Yeah.
This is the same thing we just did in that chart.
We're gonna double check just to prove it.
Alright, but it's like
We're gonna make sure, okay? Because some people like the chart way, some people like the mathy way. You guys ready? Do everybody have it written down? Oh, come on, you're killing me.
Sorry. I did.
You do. Oh, well, Gabby has it. Stop the press.
Already started.
Stop the presses.
Alright, okay.
You good to go? Hold on, I just got in trouble for not putting in my attendance.
you're gonna email it.
Something in your what?
My attendance yet.
It's only been 20 minutes.
Will you put, make sure you have your calculators out. Yeah, oh, how am I gonna do it without no calculator? There's one up in that bucket up on my desk. So let's go ahead and do the same thing.
Kaylin's always forgetting.
Let's do the same equation since we already know what the answer is going to be. So for A is the final amount. That's what we're solving for. So I'm going to say A is equal to, how much did we start with? 1.0 grams times 1 half. The T is the time. How much time has passed? 90 years divided by 30 years. And when you plug it into your calculator, let me know what you get. 0.125.
And then times 1.0 is
0.125 grams,
Yeah.
right?
Do I have to?
And then it would be 0.13 grams. Make sure you have your unit. Helios, make sure you have a unit. Okay? Don't want to lose a point for no unit. Do you see how that way, it's the same thing either way? So for those of you who are like math haters, you know,
Miss B would be disappointed.
Miss B would be disappointed.
I shouldn't put it in as the I shouldn't put the one thing in as when I put the power, the exponent in as 90 over 30, it didn't work. Because
Why? Did you not use parentheses?
around the exponent?
Yeah.
So
You have
around
to use
the exponent
parentheses.
numbers.
You have to use parentheses.
Otherwise, I can just say that it's 3 because I know that. Right?
Do you want to do another one?
Yeah.
Gabby says, yeah, let's do another one. All right.
There you go, good. Right, it's like a grade. Be real with you.
So, like, at the end of the day, like, the 2222 doesn't matter.
It's just telling you which isotope of radon it is. It's its name. It's like saying Gabby. But instead of saying just Gabby, I'd say Gabby C. Okay? So it's just labeling which one we have.
I've been asking that question my whole life, Diane. Exactly.
Michelle, could you answer that question for us?
I didn't hear.
Where's our African friends?
Whoa! We're like, yep. Jamaican. That's the wrong time.
All right, so the half-life of radon 222 is 3.8 days. How much of a 100-gram sample is left after 15.20 days? So, first thing we can do is we can do the chart way. Who wants to do the chart? You want to do the chart, Zach? All right. Ah. First thing we need to do is figure out how many half-lives have passed. So I'm going to take the time passed, 15.20, divided by 3.8. And what do you get, Zach?
So you get 4.
So 4 half-lives have passed. So I'm going to have half-lives here. I'm going to have amount here. So 0 is my initial. So if I have 100 here, 1, how much would I have?
Do we not know the half-life?
1, you would have 50.
Mm-hmm. We do know the half-life, 3.8 days.
2 is 25.
Uh-huh.
3 is 17.5.
No, 12.5. And 4 is
4 is
6.25. So how many grams are left?
62.25 grams.
With an extra zero.
Okay.
But if you want to do 6, it would be 6.
No.
What if you
You
do
have
this?
another zero. That's 4.
Oh, but you're.
All right. Who did the equation?
I did.
And did you get the same thing?
Yes.
All right.
But that's not the right number of sig figs.
No, but you know how to do sig figs, right? Let's do one like this, because you guys are, you're pretty pro. I'm going to go ahead and let you get started on your homework. Gabby.
Is it going to be about this?
No, it's actually about something we've never even learned.
Would it be 6.3
I meant
with
just
sig
like a
figs, right?
number.
No, it would be 6.250.
Why?
Because you don't want to change the number.
What about Daifu's?
No, but I mean like with the sig figs.
Yeah, that's why.
The 3.8 days, that's an exact number.
Initial 1 0.
Wait, 3, but.
The 3.8 is the exact number.
So you would do.
The 100 grams, that's a measured amount.
Well, it'll always be the.
So you just do it.
It'll always be the mass.
It'll always be the mass? Okay.
Yeah.
Good way to remember it.
That's what I was thinking.
See, I'm not good with the sig figs and the weird and the counted and the.
I still don't get why the other one was the one on the quiz.
I can show you.
for gold.
Mm-hmm.
The equation is A
Oh, you said
No.
decay in there, wasn't it?
times 1
Mm-hmm.
to the power of time over half-life.
How long is it?
Yeah.
We took yesterday.
15 minutes.
I started now.
It's in the library
Is this
or wherever it is, wherever study hall is.
do I have time to go get it and start it, or should I just wait until next week?
It's up to you.
Do you mind if I go get it?
No, you can go do it there. They'll make you do it there because they won't let you take it.
Do I need a calculator?
Yes, you need a calculator and periodic table. All right, so this one says if 100 grams of gold 198 decays to 6.2500 grams in 10.8 days, what is the half-life of AU 198? So Zach, you're my chart fan, right? So how are we going to do this in the chart? You don't know half-life, but you have enough information to solve it in the chart.
Right.
Because I know if I start with 0, how much do I have, Zach? Initially, I have 100 grams,
Yeah.
right? What do I need to go all the way through to? 6.25 grams. Can you keep doing half-life to keep doing that? Jenny, what are you doing?
I'm trying to search something about
Okay, well, can you wait and do it later? Do you have the answer to this? Okay. So if I do 50 grams here, 25 grams here, 12.5 grams here, and then 6.25 grams here. So that's 1, 2, 3, 4 half-lives have passed. And there are 4 half-lives. Well, no, that tells me how many half-lives. They want to know what is the half-life. It took 4 half-lives for it to get there. So that means that there in 10.8 days, there were 4 half-lives.
10.8
Divided by 4 equals what?
equals 2.7.
2.7?
Yeah.
So 2.7 days would be your half-life.
Wait, so is it
2.7
12.5 or 12.8?
12.5.
So our unit is days, right?
Mm-hmm.
Okay.
So in this question, if they were asking the sig figs,
You would have what? 1, 2, 3. You'd have 3 more zeros after the 2.7.
3 zeros?
I think so. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 1, 2.
Oh, okay.
Got it?
Got it.
All right. Any questions about how to do these problems? So remember, for your test, as far as your test is going to be atomic theory, atomic structure. Hold on. It's going to be atomic theory, atomic structure. Remember the calculations for average atomic mass? You're going to have nuclear equations and half-life. This is math, this is math, this is math. Atomic theory and atomic structure aren't math. That's atomic theory.
Yeah, that's the science, right?
Right, yes.
Wait, to the bottom for your math.
Yeah.
And then the atomic structure would be
Protons, neutrons, electrons, their locations, their mass, how do you calculate them? I'm going to give you your homework and then I'm going to go ahead and put on the board your extra credit for your test on Monday, okay?
Thank you.
Any questions?